Hello, everybody. Welcome to this webinar series on 6G flagship research visions. So today's topic is this based on our white paper, Broadband Connectivity, scoring the Terabit per second goal. And the speakers I will be starting opening and then followed by Josep, Emil, Italo, Tommy, Stefano, and Chinching. You can see the different topics that they will be covering. And there are a few more things that you should know. In Zoom, please use your full name so that we can know the details. And then in the Q&A that we have at the end, please write your questions in that Q&A window, not in this chat window. And then, this will be at the end, we will be answering the questions. And of course, we will record and everything will be available later on. So the topic today is this one. I'll very briefly give a very short view of what we are thinking of these 6G use cases. As you can see, we have this extreme capacity, enhanced hotspot device to device and connectivity on this remote connectivity, and then high mobility, multisensory, and this at the end you have this industrial automation and autonomous mobility. So these are quite well known things that are going on, I think, in different in terms of research directions, and you can also see rough ranges and bit rates, etc. So based on these use cases, we also anticipate this set of KPIs. Of course, the main one is at the top, comparing this 5G to 6G, and that's why we mentioned 1 terabit. But this is not the only thing by any means. There are other things, for example, mobility and latency and energy efficiency, those kind of things that we need to concentrate on. All right, so so that's very shortly to introduce this possible use cases and KPI. And now, of course, the idea is to keep this discussion going, and I will now invite Josep to start his presentation.
Okay. Thank you very much, Nandana, and once again, welcome everyone. My name is Josep Jornet. I'm a professor at Northeastern University, and in the next 10 minutes, I'm going to discuss what are the spectrum enablers for 6G with a specific focus on the terahertz band. So at this point, after Nandana's introduction, I think that we all agree that what are we trying to achieve? So we're not only trying to connect more mobile devices, but we're also trying to support faster connections between those devices. While the goal for 5G has been 20 gigabits per second, as Nandana just mentioned, the goal for 6G starts, or the goal is at least 1 terabit per second link. The question is, how are we going to support these data rates for all these devices? And well, the first way that we can think of doing so is, well, let's look into what resources do we have. We already know that in 5G, right, and when we think of the spectrum for 5G, we mainly have 2 chunks of frequencies, the sub-6 gigahertz or FR1, and then the millimeter wave from 24 to 52 FR2. Release 17, which is coming soon, is expected to extend this FR2 from the 52 all the way up to 71 gigahertz. Then the question is, where will 6G lay? Well, we could spend the entire day thinking about that, but we're going to summarize the discussion with one figure. If we think for a second, this is a frequency axis from 0 to beyond 10 terahertz. If we think of all the wireless services that we're utilizing today, I would say the majority are under 10 gigahertz, but even up to 100 gigahertz, pretty much everything has been already allocated. If what we want is more bandwidth, because we think that that's a way that we can get to those terabit per second link, well, one answer would be to jump to the optical spectrum. And yes, as we describe in our white paper, we think that optical wireless communications will play a role in 6G, whether it's in the form of infrared radiation or free space optics, mainly based on lasers, or in the form of visible light communication, again, usually utilizing cheaper LEDs. But the question here is that why would someone who is looking for resources skip this range between few hundred gigahertz and up to a few terahertz that we know as the terahertz band, or maybe you have also heard the term sub-millimeter wave, just because our wavelength is less than 1 millimeter. Well, that's the terahertz band. And that's where we think that there are many opportunities that we don't want to miss in 6G. Of course, the first ones that come to mind are in the terms of communications. And look, when we started working on this 10 years ago, we thought that we would only have little power. So terahertz would only be good for personal area networks, maybe local area networks if we get lucky. But the reality is that, as you will see in a couple of slides, technology is evolving very quickly. And today, several groups, including our own group, we have demonstrated very long terahertz links. And by very long, I mean more than 2 kilometers. So we can think, for example, if all the users are moving from higher frequencies, higher data rates, someone needs to aggregate that. So for example, wireless backhaul would make sense. And while you may think that now I'm dreaming, well, we will talk also about a little bit the application of the terahertz band above the atmosphere and their use, for example, in inter-satellite communications or space networks. You will see why. Beyond communications, however, there have been many other uses of the spectrum of the terahertz band. And some of them, are mostly related to sensing. Sensing does not only mean higher resolution and higher accuracy radar or localization. That's very old-fashioned, that's very traditional sensing. Sensing at terahertz frequencies means to leverage the unique electromagnetic signature that different materials have at terahertz frequencies. And actually, for many decades, terahertz radiation has been used, for example, for identification and classification of materials in a non-damaging way. And going back crazy, well, I suddenly mentioned Earth and space exploration. No one should be surprised that actually at this exact same time, as we are talking here, we have satellites orbiting the Earth, which already carry terahertz radios on them. Those terahertz radios, however, are not to transmit information from a user, are actually to extract information from the channel. And that's already happening. All these applications I'm mentioning are mostly in what we would call macro scale domains, but do not forget that indeed at terahertz frequencies, smaller wavelength, potentially very small antennas. So there is a huge community working on the use of nanoscale or micro scale, if you want to call them, terahertz communications for things ranging from chip-to-chip communications to maybe providing connectivity to new types of biological, chemical, or physical nanosensors, which again, they may sound a little bit crazy for some, but no, these have been developed for over 30 years now. And all these glued together in the context of the Internet of Things. Fine, so at this point, hopefully you agree that there are opportunities that you don't want to miss, and these come from the terahertz band. The reality, however, is that there are many challenges too, across different elements, from materials and devices all the way up to standardization. And what I'm going to do in the remaining of these 5 minutes is to go in a bottom-up approach to say what's real, what's not, what has been solved, and what still needs to be solved. So if we start from the very bottom, traditionally, it has been very difficult to get your hands into a terahertz radio, mainly because it has been very challenging to generate, to modulate, to efficiently radiate, and then to detect and demodulate terahertz signals. It was so difficult that we usually refer the terahertz band as the terahertz gap. But the reality is that today you can have access to terahertz radios. Commercially even, you can ask me how to get them. I can point you to the right vendors. And in the lab, we have some radios, for example, from Virginia Diodes. We also collaborate with NASA. We have some radios from them. These are real radios. They are not ready to be embedded in your phone just yet, but technology is evolving super quickly. It's not just the comms people, the ones doing research. The materials, the device, the physics community are working very hard. And even in our group, we're already working on what we think is going to be a transformative technology for terahertz, which involve, for example, utilizing graphene plasmonics to make super small antennas and transceivers, maybe antennas that we can embed in, let's say, maybe Emil will tell us, an ultramassive MIMO platform. Having said that, of course, with all this, we can make a testbed. And once again, today, we are much beyond that just making testbeds for channel sounding. That's something that was done 10 years ago. Today, we already have platforms in which we can transmit user-defined data, and we are very close to have a real-time networking platform too. So things are happening. Do not be deterred, do not be discouraged. Then you will say, sure, fine, the technology is there, but the channel is horrible, Josep. Why do you waste your time? Well, let's just think about that, because actually, it might not be the nicest channel, but it's much better than what people think. Usually people, when they think of the terahertz band, they think of the absorption losses and they get discouraged. Look, in this frequency, in this figure, I'm showing the losses as a function of frequency. The solid lines with these spikes correspond to the absorption losses, which are mainly created by water vapor molecules that start shaking when we radiate terahertz signals. But these absorption lines, appear at some frequencies. And between those frequencies, the absorption can be very low. So as long as you know which frequencies you want to use and you pick them smartly, absorption is not really the main problem. There are some problems. And for example, weather conditions will affect these absorption lines, not the position, but how wide they are. But still, if you ask me, compared to optics, we're much better. Of course, does this mean that the terahertz channel is great? Well, let's don't run. As you know, the higher the frequency, the smaller the wavelength, the smaller your antennas. So for a given power density, your antennas can intercept a smaller fraction of the power. Therefore, what do you have? Well, therefore, if you just take the free path loss equation, you will see a huge loss. And indeed, we have very high spreading losses that we can overcome in different ways. One option would be, for example, to move into fixed directional antennas. And for example, in this figure, this is actually a accurate link budget analysis in which our target is to ensure a bit error rate of 10 to the power of -6 for a given modulation scheme with a given bandwidth. That's how much gain you would need. And I'm talking, for example, that if you're fine with 40 dB gain antennas at the transmitter and at the receiver at the same time, you can easily go beyond 100 meters and close to, a kilometer if you want to push it a little bit more. You could go with directional antennas, but at the same time, we think that you can do much better. And for example, 4 years ago, we first thought, look, utilizing this new technology that we are doing, this plasmonic technology, we can actually integrate many of the elements at once. Not because we are bored, just because we need them if we want to see meaningful powers. So that's a way, and you will hear plenty about how you can take this to massive MIMO, ultramassive MIMO to make it actual work. The other problem, however, is that we don't go through many things. It's not true that we don't go through anything. No, we can go actually through some plastics, through paper, through cloth, but we are blocked easily by other elements. So of course, whenever there is blockage, you need a way to overcome blockage. And for example, today you will also hear about the use of intelligent reflecting surfaces. In our vision, it's not just a surface what needs to be intelligent. What you need is an intelligent environment, but more will come later today. Having said that, it's like, okay, the technology is catching up and the channel is not that ugly if you know how to use it. Then how do you maximize the utilization of, let's say, 50 gigahertz of bandwidth? Well, you tell me. You can scale up OFDM, or maybe you can come up with something better. For example, if we are friends with the sensing community, the utilization of very short pulses, less than a picosecond long, it's kind of popular. Maybe for short distances, that makes sense. Or we have this unique distance dependence bandwidth because of the absorption. Maybe we can come up with new modulations that turn absorption into a way to facilitate multiplexing in space and in frequency. Fine, why not? Of course, many times you may not this 100 gigahertz of frequency. You don't need 100 gigahertz of bandwidth. Maybe you can throw in some concepts from spread spectrum. That could help us. There are many opportunities for anyone with a good idea with what we do with 100 gigahertz. Of course, do not forget, we're trying to do this with not the most stable clocks while transmitting really fast and with directional antennas. So synchronization in space, time, frequency, and phase, it's a challenge. Things get even more interesting when you go above to the protocols and networks. I would say usually when we teach networks, we say that bandwidth is the main constraint. Well, bandwidth here, it's almost the only thing that it's not a constraint, but everything else is. How do you network devices when they are using very directional systems? all the time. We cannot play the trick as in millimeter wave frequencies that we say, no, for a while we're omnidirectional. No, when you go to terahertz frequencies, if one of you is omnidirectional, forget about closing the link. So we need better and fresher ideas. And as I said, we are not the only ones who like the terahertz band. The passive users, the sensing community have been there before. They have claimed some frequencies, not many, but just enough to break the beauty of this terahertz band. So we need to find efficient ways for us to share the spectrum across areas in space, in frequency, in different ways. So there is a need to explore these too. Finally, maybe we have not done a very good job, but in fact, again, terahertz communications are real. There has been a standard from the IEEE 802 family since 2017. But of course, we need more. And to convert something from a Wi-Fi type to a cellular network, there are many things that need to happen, many things in which many of you, I hope, can contribute. So with this, just saying, we're going to see many solutions in the rest of the day today. Those solutions may play across frequencies. Do not ignore the terahertz frequencies. They are a real contender with challenges, but with many opportunities. That's it. Thank you.
Thank you also for nice presentation on this terahertz and possibilities there. And we move quickly to the next one with Emil. Just before starting, Emil, just to remind the listeners to send the questions in this Q&A so we can answer later. Okay, go ahead, Emil.
Thank you. So it's great to see that so many people are here and listening. So I am going to talk about ultra-massive MIMO and giving it a maybe broader definition that Joseph did in the previous talk as well. So we'll talk about the vision and the different embodiments. I will talk about one of those, and then two of them will be the focus on later presentations today. So massive MIMO and ultra-massive MIMO, what is this really about? Well, let's just briefly start about what is the state of the art in massive MIMO. So now there are 1 million base stations, I think, that is using 5G, and a lot of them are in China, for example. And these ones are essentially all of them in 3.5 gigahertz band, where you have like 64 antenna integrated radios, which we typically call antennas. They might have a size of 1 meter times half a meter. And what do we use them for? Well, we could utilize the beam forming gain, the directivity, so to get the strongest signal to users. And then we can serve multiple use at the same time and frequency by sending different beams towards them. This is the spatial multiplexing, and this could also be utilized to send multiple signals to the same user that have multiple antennas, either with different polarization or with the same polarization, but separated, so we can multiplex signals. But even if we call this massive here, it's sort of massive in size. It's not massive in size, it's massive in number of antennas. So if we zoom out here, we can say that these massive MIMO panels, when we put them up in the roof top, they will look fairly small for you as you use it down here. You will see a beam coming towards you, but even if there are many active antennas inside this one, it will be electrically small, which means that it doesn't fill out your entire field of view. It just will be somewhere up there, and then it has some adaptivity. When we talk about ultra-massive MIMO here, it's of course about having many more antennas, but also the potential of making them really electrically large, which would then mean that they fill up a substantial part of your field of view. It doesn't need to be a dense array where there are antennas every centimeter. It could be spread out, and we will look at different options like this. So one of the goals of this entire seminar is to talk about how we can reach this 1 terabit per second goal. And there are different ways that you can reach this one in different types of situations. So just to understand this, let's look at the capacity of a communication system measured in bits per second. Here's a typical formula. You have this log 2R1 plus a signal to noise ratio, and then there are two factors in front of that one. So what we have here is the bandwidth. So obviously, if you have more bandwidth, you are getting something larger in front of here, but it also increases noise power. We have the beamforming gain here, which is giving us more received power for the same signal power and mitigating the propagation losses. And we have the multiplexing of layers here. So there are essentially 3 ways that you can improve your capacity. You can multiplex more signals to one or multiple users. you could use more bandwidth. So if you increase the bandwidth here, then you're also increasing the bandwidth here. You get more noise. You integrate over the larger part of the frequency domain. So you need to compensate for that somehow by either reducing range or adding more power or adding a larger beamforming gain. And Joseph was mentioning this beamforming gain as one of the options as well. Or you can just live with reducing your range as well. But in general, you sort of need to have a little bit of all of these different combinations. And if you are really wanting to have very high terabit per second range for one user, then you probably need to go up towards much more bandwidth. But I will show you now that you can reach 1 terabit per second in a cell in different ways. So let's focus on that case. Considering a typical 3 gigahertz band, 50 megahertz of bandwidth. And in this low band, here is a sum rate that you can achieve measured in terabit per second. So if you are at 1 or larger, you have scored our terabit per second goal. And we see different number of antennas, different number of users here. And yeah, you need to be up here serving a huge number of signals, multiplexing them, and you would need to have a lot of antennas. But the good thing with a low band is that if the user is not moving on very quickly, you will have a huge channel coherence. You have a long time to learn the channel, then you can serve them. So suppose you put up a base station on the top of the skyscraper I was showing before, and then you have 10,000 people in Central Park. Then you can spatially multiplex all of them. So that is one option if you would like to reach this in the low bands. Then if you are going up, here I've gone up 20 times in frequency and using 20 times more bandwidth. And in that case, you see we can also reach 1 terabit per second. Now by having few users, still a large number of antennas. And as you go up further and further in the frequency domain, yeah, you can give this 1 terabit per second specifically to a particular user eventually. So you can reach this in different bands. All of these frequency bands will be useful for different types of applications, low mobility, high mobility, a lot of users, few users, and so on in the future. And when we are putting up a lot of antennas, I think it's important to know the fundamental limits, something called the spatial degrees of freedom. So for a particular antenna, there is a certain number of layers or signals that you can spatially multiplex. And just to not go into too much mathematics, it's sort of how many signals eta that you can transmit while controlling interference. So you essentially get that eta times log plus 1 plus SNR. And this is sort of saying how many signals you can separate with your array. And it's a bit like sampling a band limited signal. You know, if you have a band limited signal, you should sample it at least twice per period. And in the same way, if you have a space limited array and it samples the signals that are propagating over there, how much can you separate? How many signals can you separate? Well, if you have a plain array of length L and height H, L times H, then eta is approximately equal to this. You take the length and the height, and then you have a scaling factor here, pi divided by lambda square. Lambda is the wavelength. So say, for example, we go back to this skyscraper case here. You have a 10 meter length here and 30 meter height. And if you fill this entire space with antennas for the 3 gigahertz band, then this will be around 100,000 elements, or 100,000 signals that you can spatially multiplex, which is far beyond what you ever would be able to do in reality. So sort of the physical limits is far above the number of users that will actually be in front of the skyscraper. So it's the richness of the channels, the number of users that are there, it's a limiting factor, which also tells you that you don't need to fill this entire space with antennas. So if you would like to put up a large number of antennas, there are 3 potential embodiments that I am describing here. One is what we call cell-free massive MIMO, where you take the antennas and you really spread them out over the environment. And Stefano is going to talk more about that in a dedicated talk. Then we have the idea of intelligent reflecting surfaces, where you gather a lot of elements in one space, but you are separating it from the transmitter and the receiver. And the signal that is coming from one location, then you can control how it's going to be reflected. And this is another embodiment that will be covered in a specific talk. And then the third embodiment is this like really electrically large co-located arrays that I was mentioning over the skyscraper, for example. And how can you implement something like that? Well, as I was mentioning with this spatial degrees of freedom example, you probably don't need all the degrees of freedom that you could achieve by putting up something like this. You can have the high space in between, or you don't need to sample all the elements that you put up. And this is where the concept of holographic radio, which is another name essentially for what Joseph was describing with the nano antennas as well. So the idea here is that you have a surface with elements that could change the signals. You have a radio unit connected to it, and we can call this a meta surface if you like to. And the signal coming from the radio unit, it goes into the surface, and the surface is phase shifting or time delaying the signal different ways. You can form one beam in this direction, and then another point, you change the phase shifts here and you form a beam in another direction. And what's really going on here is that each element is a passive patch that gets the signal from behind. You have a diode that is controlling the impedance of the signal, and that is sort of determining the phase delay, and in that way, in which direction the signal is going to propagate. And why do we call this holographic? Well, this phase shift pattern here that is determining in which direction the signal is going is like a hologram that is describing how the propagation environment is going to be affecting the signals. And the radio unit here from behind can then, if you have multiple signals, you can either try to send multiple of them from each element, or you can divide into different pieces and send different signals from different ones. And by having fewer radio units than you have elements here, you're also sort of cutting down on the spatial degrees of freedom that you're actually going to utilize. And just as in holographic recording, it's sort of you use uplink parallel to user send a signal, then you record the best type of phase shift pattern here for a particular user, and then you use it when receiving, and when you transmit, you do the opposite type of thing. That's also the analogy to holographic recording, in this case, radio. So I'm about to wrap up here, but people who have been interested in how to build new type of MIMO arrays might also have heard about the concept of orbital angular momentum, or OAM. And you might wonder, why didn't I say anything about that? Well, it is a nice electromagnetic concept, which is sort of about you have two different circular arrays, and you are sending signals, and then you can generate wave signals that are spinning in particular ways, and that is the angular momentum. However, this is not an additional dimension. It doesn't increase the spatial degrees of freedom in any particular way. It's just that if you have arrays of this type and put them up in a particular way, then if you do everything typical MIMO, you will observe this type of signal transmissions. So it is a nice feature, but you don't need to explicitly try to utilize it, because it will be utilized automatically if you do MIMO transmission. So with that, I will wrap up and just take the opportunity to mention my podcast, Wireless Future, where we were just uploading the second episode today.
Right. Thank you, Emil, for the nice discussion on this ultramassive MIMO, holographic, and those topics. And next is Italo. Please share your slides.
So, good evening, everyone. And I will take a step back now from the detailed discussion that we had before from Josep and Emil. And I will talk about the differences on very high level, differences from 5G to 6G. So, first of all, while 5G wireless networks are being deployed in many countries, and the 3GPP has recently defined the release 16 and of the new radio standard, which provide enhancements to the first new radio specification published in 2018, then the research community is starting to investigate the next generation of wireless networks, which will be designed during this decade, and it will shape the development of society during the next decade. And here we have some key questions. So the first one is, the main question is, what will beyond 5G and 6G wireless networks look like? What is a very general and ambitious question, and in particular, we can ask ourselves which new technologies will be at the heart of 6G, and will the 1 Tbps frontier be reached in practice? 1 Tbps is the peak data rate objective in particular. And will the uniform coverage all over the world and quality of service be fully achieved? So, well, at the moment, it's very challenging and risky to provide definite answers to such questions. But we will try, nonetheless. So, first of all, I will provide a conservative answer. Okay, this is the result of a long brainstormings with our group of colleagues who produced the white paper on broadband connectivity, and the conservative answer is 6G networks will be based on a combination of 5G technologies with other known technologies that are not mature enough to be included in 5G. And this means that any promising technology that would not be included in the standards in the next few years can potentially be a candidate technology for 6G. And for example, full MIMO processing with digital signal space beamforming, although it has been known for many years now, has not been fully embraced so far in favor of the more traditional codebook-based beamforming. Then we have a more daring answer. So 6G networks will be based on new technologies that were not at all considered when designing and developing 5G. And this will be combined with vast enhancements of technologies that were already present in 4G and 5G. So the example here is that we can combine ultramassive MIMO, which has been just described by Emil, which is basically an advanced, very advanced version of the massive MIMO that is already present in 5G, with the entirely new concept of cell-free and user-centric network deployments. So what we are confident about is that 6G networks will include the following features. So first of all, they will be based on extreme network densification to form a cell-free network with seamless quality of service over the coverage area. And this will include different types of access points, massive MIMO or ultra-massive MIMO, intelligent reflecting surfaces, and cooperative coordinated transmissions. Then it will complement sub-6 gigahertz carrier frequencies with higher frequencies beyond the millimeter wave bands through the terahertz band and visible light bands for higher capacity point-to-point links. This has been discussed by Josep in detail. Then it will integrate terrestrial and airborne and satellite networks to improve coverage and offload the terrestrial network. And here UAVs and low Earth orbit satellites will play a role in extending the coverage to remote areas. Then it will make intense use of distributed processing and cache memories in order in the form of, for example, cloud run technology, and will leverage network slicing and multi-access edge computing to support vertical market. And finally, it will also exploit machine learning and AI, artificial intelligence, to improve the efficiency of traditional algorithms for signal processing and resource allocation. So this is our view on what 6G will be with respect to 5G. So today 5G is the first 5G, we can say, is the first wireless generation that truly makes use of multi-antenna technologies. And from 4G to 5G, the peak data rate has increased by a factor of 10 or 100. We will see about that. And this trend is expected to continue in 6G with peak data rates up to 1 Tbps. So 3GPP defines massive MIMO for 5G in the new radio standard as having more than 8 antenna ports. And this is widely supported in the current standard, but of course, these numbers will increase a lot in the next few years, and they're already increasing as there are plenty of commercial products with up to 64 and even more antennas in the sub-6 gigahertz bands. Then at millimeter wave frequencies, the 5G new radio standard currently relies on larger antenna arrays and analog beamforming. And here we have from 8 beams in 1 dimension at sub 6 gigahertz frequencies to 64 beams in 2 dimensions, so vertical and horizontal at higher frequencies. So I was just checking the chat in case of some connection problems. I would just mention about this multi-antenna techniques that Release 16 also supports transmission from multiple transmission reception points, TRPs, and several other enhancements to exploit large antenna arrays. So the future is that even during 5G, the next releases of 5G, the number of antenna will increase and the importance of multi-antenna techniques will increase. And for 6G, this trend is expected to continue. This 6G will push this aspect much further by including ultramassive MIMO, holographic radio, intelligent reflecting surfaces, and coordinating transmission from multiple access points. So here we take a brief look at the use cases of 6G, and Nandan already mentioned briefly these use cases. And here we have that the emergence and the need for 6G technologies will be driven by unprecedented performance requirements arising from exciting new applications which cannot be supported by existing cellular networks. And broadband applications will require high data rates in combination with other specialized characteristics. And here we have some examples of use cases which will complement existing use cases by 4G rather than replacing them. Okay, so first example is extreme capacity XHAL. Here we have a fixed high capacity point-to-point link capable of aggregating data from many users and providing efficient access to cloud and edge computing resources. The second use case is the enhanced hotspot, where an access point with high downlink data rate and short coverage to several provides coverage to several low complexity users with very high data rate requirements, but not many other requirements. Another use case is the short range device-to-device communications, where high data rate links will be implemented between low energy, low complexity users with limited or no involvement at all by the network. And a very important use case is connectivity in remote areas, and 6G will aim at guaranteeing 10 megabps in every populated area of the world by combining terrestrial, airborne, and satellite networks. Also, high mobility is very important for 6G, and mobile hotspots will arise from fixed infrastructure to planes and high-speed trains with very high data rate, low latency, and close to 100% availability at speeds of exceeding hundreds of kilometers per hour. And there will be many multisensory applications and extended reality, which capture multisensory inputs and provide real-time user interaction. And industrial automation will finally be further enhanced with respect to 5G and Industry 4.0, and high precision manufacturing will be enabled by very high reliability and low latency and real-time data transfer. And lastly, autonomous mobility will allow full autonomous smart transportation thanks to high data rate, high reliability, low latency, and 100% availability at speeds up to 1,000 kilometers per hour. So these are very ambitious targets, and therefore the KPIs are also ambitious. But we can mention that the KPIs have mostly remained the same from 4G to 5G, and the requirements have just been made sharper. And one exception is the energy efficiency, which was introduced in 5G, but without specific targets. And except for some additions, the current KPIs for 6G are mostly the same as for 5G, but of course, with much higher ambition. However, in the future, we should consider new KPIs, which are driven by technology, productivity, and sustainability societal aspects. For example, it would be meaningful to include or introduce new KPIs related to cost efficiency for remote areas and environmental aspects. environmental impact and so on. So 5G introduced 3 service classes, as we all know, which are quite rigid, but they are already improvement with respect to 4G. So we have MEB, enhanced mobile broadband, URLLC, ultra reliable low latency communications, and MMTC, massive machine type communication. So these classes have some quite strict KPIs within each class, and only one of them is a broadband type of traffic. So 6G, in 6G, we'll move from a situation where broadband connectivity is delivered in a single way to a scenario where the requirements are of broadband applications will become so diverse and specialized that we can only accommodate some of the requirements for each application. And to accommodate such requirements, we will need the 6G networks to be reconfigurable in real time. And for example, without going through the whole list of KPIs, autonomous mobility, just to cite an example, will require only a handful of these KPIs, and namely high experienced data rate, high reliability, low latency, and high peak data rate, or high connection density. So this concludes my talk, and I leave the floor to the next speaker. And some of these topics that I mentioned will be discussed in the next talks, such as self-remote.
Thank you, Italo. So for your comparison with 5G and 6G, so let's go to Tommy. Please share your slides.
Thank you. Okay, I hope you can see my slides and hear me. So I would like to talk a bit about lower layer enablers for agile and efficient and dense wireless networks towards 6G. As a starting point, I wanted to recap where we were and are going. So 5G and beyond, I think we're in 4G, we did the big step from internet to mobile internet. In 5G, we enable rich mobile internet and wireless internet of things. We open up for robustness, low latency, and internet of skills. There's still work to be done here in academia and in industry to make this really happen, but there are enablers in the standards partly now. So what about 6G? I'm quite convinced that the AI will be a very important part of 6G, any applications using mobile networking. In particular, because we can make skills available on a much bigger scale. So by doing that, some skilled people can train AI agent, and that means that this availability can get better because we are not limited by the speed of light. And by doing that, we can also duplicate. So this is a way to make a more democratic availability of the scarce resources of skills in the world. So I think we have a great opportunities there. But by doing that, we also can run this out in the mobile network. So I think there will be a convergence on computing, communication, storage, and artificial intelligence towards massive and distributed, that is local Internet of Skills. So what that means, I think it means that we need to do research to do holistic research based on holistic performance metrics, taking all these aspects into account and find optimal trade-offs. We need to cross borders. But it also means when we do these bigger problem formulations, we also maybe ourselves need to adopt ML and AI techniques to try to understand, splitting the layers in a non-orthodox way, and try to learn what are the real problem formulation and how to split the problem in a new way, and go back to theory and try to understand what we actually did. So metrics like end-to-end latency, end-to-end security, total efficiency, sustainability, and there will be many metrics we need to develop here. Both Nandana and Italo talked about the use cases that we have in our white paper and there are many works going on in the world on developing use cases as well as KPIs. So I will not repeat them, but from my perspective, I want to make a few notes. I think that not all code KPIs will need to be supported simultaneously in a given use case. However, many applications will need a certain combination of KPI values. And to meet overall metrics such as total energy consumption, security, and sustainability, we should target to just meet service-related KPIs. We shouldn't overdo them because they are very costly to meet. And it's also very likely that 6G will, to a large extent, carry information related to non-traditional applications of wireless communications, like distributed caching, computing, and AI decisions. So we should be open and interact to develop potential new KPIs that we haven't thought about so far in the 5G and early 6G era. So I just wanted to make one quick illustration of what I mean with a little bit more holistic problem formulations. And this is old work we did, and it's not as broad as I really think we should do in 6G, but just to tell you what I mean. We did an minimization under service constraint in millimeter wave cooperative communications. So we had a heterogeneous network with some macro base station and small cells, millimeter wave powered, all 1 millimeter wave. So they should jointly serve a certain number of users to mitigate blocking and implement load balancing. And there could be standalone or non-standalone. So we drive close to optimal, fully digital and hybrid beamforming schemes, but we did it by minimizing the sum power subject to per user spectral efficiency constraints. So the users maybe had a KPI in their service level they wanted to have a certain spectral efficiency, but that we put in the constraint and the objective function we put to minimize the total power instead. And that we did by including both hardware and RF transmit power consumption. And they were enabling sleep. So it was a joint optimized freecore, load balancing, and base station operation mode. And very quickly, I will show the trade-offs here. So the first upper plot, you see some RF power use, and if we have fully digital beamforming and no sleeping, we need the least RF power. If we do hybrid beamforming, we need a little bit more RF power. And if we enable sleep mode, we need even more RF power. Oh shit, it's not good. We are using more RF power. But come on here, look on the lower plot. We are saving in the total power consumption because we enable sleeping, and hybrid beamforming need less hardware power than fully digital. So overall, hybrid beamforming with optimized sleep patterns have a total sum power that is the lowest. The same goes when we are densifying with a number of small base stations in this area. The more small base stations we have, the less we have need for the macro base station to help out. And also in this optimal approach, with the more base stations we add, the less total power consumption we need, because we are densifying and the path loss is the biggest challenge. So we have many speakers today, and we talk about many of those things I will list now. So I will just show on one slide some of these key enablers, and there are more to come for sure the coming years. We have the spectrum flexibility that in particular Josep emphasized earlier. Emil and emphasized the need of antennas, and here we can look on trying to find the optimal carrier frequency for different deployment scenarios. We have introduced intelligent reflecting surfaces or RIS, and there will be more talk about that later, I think. And I know Stefano after me will talk about distributed large MIMO, and these are important enablers. But it also means a lot of densification. So the coverage on each of those will be smaller, and that means we need also to think about how to support mobility here. So I think mobility schemes will need to go towards resource allocation problems rather than a protocol on top. And we might need to get orchestration, split user control plane by looking on alternative vertical platforms to help out on orchestrating on the larger scale to enable coordination with minimized coordination overhead. And then with this spectrum flexibility opportunities, we have an opportunity to bundle different frequencies and create the diversity among the weaknesses the different frequency bands have, and increase reliability in that way. For example, joint free specs and millimeter wave. And we also need to work with spatial diversity. And this is an illustration here. This is from early millimeter wave communication times in the product Millimeter Magic. And it's still very varied, but will be much more valid in an even denser scenario. We need to think about integrated resource allocation and load balancing. And when we get access to wide system bandwidths at the upper millimeter wave, and sub-terahertz, they will be big chunks, and we should split them flexibly. So if we can pool the spectrum for both access and backhaul, we can handle dynamics here. It's a big stadium scenario, a lot of users, and then they go away. All of a sudden, a lot of communications needs over here. Maybe some are happening here with a local map acquisition for self-driving cars. So a lot of the information is both harvested and consumed locally. So there's less backhaul need from time to time. Whereas another case, there's a lot of need of communication, like from the stadium, all about streaming, what's happening. So we need to have an agility here and share the spectrum and also antenna resources in a clever way. So for this reason, I think that the integrated access backhaul in the definition now for in the 5G is even active in 3GPP now, but this in a more broad sense will be more and more important, where the heterogeneous backhaul resources. So we have worked on that. So the arguments for IRB is network resources flexibility, network cost reduction, time to market reduction, and by introducing some control interference also in the backhaul fronthaul, we try to optimize end-to-end performance metrics rather than local. So we have done some simulations based on point processes. So I don't go into all the details here, but I want to show the effects. There were simulation on 28 gigahertz. So here in this plot, you can see if we have full fiber connectivity in small cell base stations, we at the 60 in the density, we need to have small IIB powered nodes in the order of 65 or so if we have this target rate. And so we need a bit more in the densification SPS, but we can still do it. The same when if we look here on how it scales when we go from only IIB nodes to fully fiber in a fractional scale, we need gradually more. Well, the service can probability go gradually up when we go to full fiber, but we can live with this kind of level of availability. So with this bigger story, I see I'm using a bit more time. I think we need to work with high layers, because network slicing has so far mainly worked on transport and core networking. In 6G, we should go also in the 5MAC area. So we should do resource creation. So that's a EU project or it's a training network that I'm active in. So we try to work on all these aspects here. I think that 6G technical enablers, we have heterogeneous spectrum, massive connectivity, and we should embrace this opportunity for 5MAC network slicing enablers. ADR multi-connectivity, ADR duplexing schemes, non-orthogonal massive MIMO, 3D channelization, adaptive numerology and ADR waveforms, IIB, and a lot more. So this, I think, is another interaction we need to do, and coming from the 5MAC area, and look on higher layers and actively interact to make things happen. So finally, I want to do a comment triggering on Josep's presentation. Terahertz is much more than communications, and there's a big opportunity with the mobile communications community going there for all the other industries too, because we have massive scale. So I think from the bigger problem formulations, joint sense communication, all the other application areas here, we should interact and learn and try to do generic solutions. So with that, I just want to say, I think the exciting times coming up here. We've been very active in EU projects over the years to make system concepts, and hopefully there seems to be something coming up for 6G as well. So stay tuned.
Thank you for your quite comprehensive presentation. So let's go to the next one. It is Stefano. Please check your time with the presentations. We are a little bit running short. Anyway, go ahead, Stefano.
Okay, thank you very much, Nandana, for organizing this really wonderful event and for inviting me. And okay, today I'm talking about cell-free massive MIMO deployments and comparison with traditional multicell massive MIMO networks. And okay, there is this slide here, this figure about the enablers for 6G. In our paper on white paper, we have divided these enablers at the spectrum level. We have considered enablers at the protocol level and the infrastructure level. And regarding the enablers among the several enablers that are here, the ones at the focusing on the one at the infrastructure level, you see all these technologies. Many of these have already been discussed by my colleagues. In particular, Emil has talked about ultra massive MIMO and holographic radio. After me, there will be Quink talking about IRS. Integrated access and backhaul was just discussed by Tommy. And okay, I'm going to focus a little bit more on cell-free networks. Okay, what is a cell-free network? Actually, the idea is to go beyond the traditional multi-cell massive MIMO deployment, where you have large base station with large arrays of collocated antennas. So you have a lot of antennas collocated, all of them on the same place, on the same spot. And the idea is just to have a very large number of low complexity, simple access points with few antennas distributed over the area. And all these access points are connected to the CPU, to a central processing unit. Okay, this is just the original formulation that was introduced in this paper by some researchers. Basically, the idea is that, okay, in place of having all the antennas collocated, we distributed them. And this architecture puts together, merges some aspects of massive MIMO, because the analytic tools that are used to analyze this system are the same that have been developed for massive MIMO system. So there is a merging of aspects of massive MIMO with cloud radio access network aspects. The protocol that is going to use is the time division duplex. Of course, this is not mandatory, but it is recommendable, because in this way you can ensure reciprocity of the channel. And the key difference between these cell-free deployments and cloud run or network MIMO models that were already known before this is that both uplink channel estimates and beamformers are computed locally. So the channel estimation is done locally in every access point. So every access point estimates the channel from the users to itself, and the beamformers are computed locally. Of course, this brings some performance degradation with respect to the case of the case in which the precoders and the beamformers are computed in a centralized way. But in any case, you still have good performance. Okay, in the original version, the one that was introduced originally for cell-free massive MIMO, it was assumed that all the access points served all the users in the system. Actually, after some time, it was recognized that this is not really the optimal way of managing this cell-free massive MIMO system, because of course, there is no point where a user that is placed here should receive some power from this access points that is very far, and so it was soon after the introduction of self-free massive MIMO, there was the introduction of these scalable self-free or user-centric concept, where every user actually is connected not to all the access points in the network, but to the ones that are closer, okay? And in this case, the system becomes scalable, because imagine that you can do a deployment on a wide area of this system, and you don't have that every access point has to serve all the several users that can be active on a wide area. And another thing that also should be taken into account that is not represented in this figure is the fact that you can have also more central processing units. Okay, so you are not forced to have all the access points connected to the same CPU, but you can have several CPU in order to have some predefined clusters. Okay, so these are just ideas that can be that are very useful when you think about practical implementation of these systems. Okay, now the focus of my presentation here is just to make a comparison between these self-free massive MIMO networks that we have just introduced and the traditional massive MIMO cellular network with collocated antennas. Okay, just from the point of view of just if you want to give to provide a qualitative comparison, we can say that the main advantage of the self-free structure with respect to the self-free massive MIMO is that you have an increased fairness across users, because of course here when you are very close to the base station, you have 100 antennas that are ready to serve you, and you enjoy very large data rates. But when you are at the cell edge, probably when you are at the same distance between your reference base station and some interfering base station, you experience some not so good performance. So this system, massive MIMO, that is a great system, but is still affected by the cell edge problem. Okay, so you have not so good performance in the cell edge. Whereas here, the concept is that the user is always at the center of the network. Okay, so there is a dense deployment, so there is a large likelihood that the user will happen to be very close to one access point. So you have also somewhat better capabilities to provide larger data rates to all the users, and of course the fact that you have the access points very close to the user brings naturally that you can realize systems with a lower latency, and you can naturally support mobile edge computing applications, and you can also equip these access points with caching and computational capabilities, so that you can do computational offload. And of course, in this case, you have much more flexibility because you have access points, so you have network terminations that are very close to the users. You can enjoy these advantages, and of course you can also have increased energy efficiency, because when you connect every user to the access points that are closer, it may happen in low load situations that some of the access points are not connected to any mobile user, and so to any mobile device, and so you can switch them off, okay, or put them in a standby low power mode, so you can have also some increased energy efficiency. Okay, I'm going to present a comparison between a traditional multi-cell massive MIMO deployment and self-free massive MIMO deployment, and in particular I'm going to present results for the case in which we have 4 BS with 100 antennas, and this is the massive MIMO deployment, and we compare them with another deployment, the so-called self-free deployment, where we have 50 access points with 8 antennas. Of course, the total number of antennas in the two cases is the same, and also the maximum power per BS and per access points is such that, of course, the total radiated power in the system is the same. The number of access points of UEs or mobile stations is 30. Okay, and we are going to consider both uniform power allocation and fractional power allocation. So in this figure, we represent the what happened, the CDF of the rates per user on the downlink. We have three systems. One is the cell-free, it is the full cell-free, where all the users are served by all the access points. The green one is the massive MIMO, and the blue one is the user-centric version of the cell-free, or the scalable cell-free. Okay, and here you have that every user is actually served by just one access point, the one that is closer. And so this actually is more similar to a small cell system, because you have that every user is served by just one user, by just one access point. And in this case, instead, you have that every user is served by the 5 access points that are closer, okay, or to which it has the largest scale fading coefficient, okay. And then we have 3 different types of beamformers: channel matched beamforming, so maximal ratio transmission. Then we have regularized zero forcing, and then we have partial zero forcing. Okay, so partial zero forcing means that you do not force to zero you do not protect against interference all the users in the network, but just a limited number of them, the ones to which you produce, every access point produces the largest amount of interference. Okay, and actually you can see how basically there is a large, considerable gap between the green curves and the scalable version of the cell-free in both situations, especially in this case. And of course, this is actually an experimental validation of the increased fire fairness of the systems. Instead, indeed, if you look around this region here, you see actually that the rates for the users that have the worst channel conditions will be larger with both the cell-free and the user-centric, and in special case, particularly for the cell-free case. Of course, in this area, the massive MIMO becomes again competitive, and of course, this is related to the fact that probably here there are the users that are very close to the antenna arrays. So in this case, of course, users can enjoy very large signal to interference plus noise ratio and can communicate with very large data rates. Okay, this is for the case of uniform power allocation. I have another couple of plots for the case of fractional power allocation. The conclusions are very similar. The only point is that, okay, we have the cell-free, the full cell-free, okay, the non-scalable version of the cell-free performs pretty bad, and this is due, of course, to the fact that with fractional power allocation, you give more power to the user that have bad channel conditions. And in a cell-free, where all the access points serve all the users, the access points spend the largest amount of power trying to connect to the users that are very far. Okay, so this is another confirmation of the fact that the full cell-free is not really, when you consider a cell-free system, you have to associate it with a good user AP association rule, so that you can have very good performance. Okay, and again, this is for the case where a user is connected to just one access point. In this case, it is connected to five access points. Okay, I'm on my last slide, and okay, so we have seen that cell-free systems in their scalable version offer substantial gains in terms of fairness and outperforms multicell massive MIMO systems. And of course, this is just in architecture, so it can be used in conjunctions with other 6G technological enablers, such as satellites, because of course you can imagine an integrated terrestrial satellite network where you have both, where you have a cell-free architecture. So mobile user can connect simultaneously to a couple of satellites and to some users, to some base stations on the ground. And of course you can extend, even to much of the work on cell-free have been carried out with reference to sub-6 gigahertz frequencies. There are also some papers that are starting considering it at millimeter waves above 6 gigahertz frequencies. And of course, it can be also used for Terahertz communications, where you can have blockages. So probably a cell-free architecture where every user is connected to multiple access points provides macro diversity. And so it can be also merged with the Terahertz communications. And of course, there are a lot of interesting and challenging problems to be considered. For instance, one could imagine how to optimize the AP deployment, how to optimize the user AP association. Here we have just considered a very simple heuristic rule where every user connected to the AP to which it had the largest channel gain. There can be the introduction of some cooperation between nearby access points. For the moment, this is out. This is, I mean, not fully aligned with the self-free philosophy, but it could be done. And of course, integrated access at the call is a hot topic, because I mean, you could imagine a self-free system where the access points have to use the same frequencies used for the radio access to connect to the CPU. Okay, so this could be another interesting and challenging topic to be considered. Okay, this is enough for me, and okay, thank you for again, and I leave the floor to to Nandana first. Thank you.
Yeah, thank you, Stefano, for a nice introduction on the cell-free and traditional multi-cell. So let's go to last but not least, to Qingqing Wu. We are a bit out of time, but anyway, so let's listen to Qingqing.
Okay, so can you hear me?
Yes, go ahead.
Okay, I got a minus 10 minutes to present my talk. Okay, so hello everyone, welcome to my talk. This is Qingqing Wu from the University of Macau. I'm very happy to have this chance to give a very short introduction on the intelligent reflecting surface. So the title of this talk is Faster and Smarter and Greener Intelligent Reflecting Surface for 6G. So as some of the previous professors, they have just mentioned some of the some basic information about an intelligent reflecting surface. And from my perspective, and in the last several decades, our wireless channels has been treated as the random and uncontrollable variables. So in this context, we propose a new paradigm shift towards 6G that is called a smart and reconfigurable wireless environment. And the main difference is that the wireless channels between the transmitters and receivers is highly controllable, and which means that in the past, we mainly optimize the transmission and reception at the base station and the users. But in the future, we also want to control the wireless channel. And the key enabling technology proposed for it is called intelligent reflecting surface. So this is one proposed hardware architecture. Basically, this IOS is to modify the signal propagation by a highly controllable reflection. So the keyword here is highly controllable. And this is quite different from our current walls and ceilings and windows that just reflect the signals randomly in different directions and also lead to substantial power loss. More specifically, it is composed of a large number of reflecting elements, and each of them is able to reflect the signal with the reflection amplitude and phase shift. And by coordinating the reflection of all the elements, we can achieve the three-dimensional beamforming towards the users, right? As we can see here. So even when the user moves, right, the IOS can still track the users, as we can see here. Even when the incident direction, the signal does not change, we can still track the users. So it's kind of intelligent, not only in software, but also in hardware. And this is a vision of the IOS-enabled 6G wireless networks, where the wireless radio environment is highly controllable and smart. In the indoor case, the IOS can be deployed over the ceilings and walls and furniture to achieve the seamless coverage. And particularly, they are very useful for the indoor scenarios with a high density of users and massive connections, like smart factories, stadiums, large shopping centers, and airport. And in the outdoor case, it can be deployed over the building facade, lamppost, advertising board, and even on the surface of the vehicles to support different types of applications. So basically, the IOS is a promising technology for making our infrastructure intelligent for 6G, and also helps achieve the future smart home and smart city. But before achieving this vision, we need to solve a set of new challenges, right? That is IaaS reflection optimization, IaaS channel estimation, as well as IaaS deployment. And for the IaaS reflection optimization, let's consider a very simple example with a multiple antenna access point and also a single antenna user, right? Here we deploy an IaaS to improve the user receive power at the user side, right? Because we have the multiple antennas at the base station side, we can leverage the traditional active beamforming, right? Like, for example, the maximum ratio transmission to serve this user. And also because we have the IaaS, we can also leverage the passive beamforming to serve this user. And particularly when the AP user direct link is blocked, for example, blocked by some obstacles, we can steer the beamforming at the access point towards the IaaS, and then let the signal bypass the obstacles to reach the user side, right? So this is a kind of concept of joint active and passive beamforming here, because the access point is active, the IaaS is passive. It has no IF chance, right? And because we have the IaaS, it is very intuitive that we can improve the user receive power, right? Because we have more reflecting paths, right? But we still want to know what is the fundamental performance limit of using IaaS for such a very simple scenario, right? And here we get some very interesting results. And we found that when the number of the reflecting elements n is sufficiently large, the user receive power can increase quadratically. As you can see here, we have a squared power gain. And here I briefly explain why. Because we have the 3-node scenario. When we increase the number of the reflecting elements here, we increase its aperture, right? Just like an energy harvesting panel, right? Solar panel, we got an aperture gain that is in the order of n from the AP to the IaaS link, right? And also from the IaaS to the user link, because we can leverage the elements to achieve the passive beamforming, right? So we can achieve the beamforming gain that is still in the order of n, right? So combine these two links together, we can get the square power gain, right? And here are some of the simulation results, right? And also this is mainly based on the continuous phase shifter, which means that the phase shifter is can be arbitrarily tuned between 0 and 2 pi. But in practice, for example, as we can see here, when we use the pin diode to achieve the phase shifter, we only have 1 bit, which means that we won't have 2 phase shifter values. That is 1 of 0 and pi, right? So in this kind of case, when we're using the low resolution phase shifters, can we still achieve the square power gain, right? This is also another fundamental problem. And we also have some very interesting results. And we found that when the IaaS is sufficiently large, and we derive the power loss caused by using the low resolution phase shifters, right? As we can see here, the power loss is given by this expression. And the first point is that we see that it only depends on the number of bits used, right? Because B represents the number of bits used. And when B equals to 1, it suffers from the 3.9 dB. And when B equals to 3, it only suffers to 0.2 dB. So it's very small, right? So in practice, by using 2-bit or 3-bit IaaS, we can already get a very sufficient good performance, right? So another interesting point is that we found that this expression has nothing to do with the number of the reflecting elements n, right? So as I just mentioned, for the continuous case, well, for that B goes to infinity, we got a square power gain. But right now, it has nothing to do with then the power loss. So this also implies that by using low resolution phase shifters and low resolution IaaS, we can still achieve the square power gain. So the answer is yes to this question. And also channel estimation is another very important problem because there are 2 main challenges. The first one is that because the IaaS, it is passive, it has no RF chance, it cannot transmit and receive pilots. And another thing is that because it is passive, we have to use a large number of reflecting elements. So in practice, this implies that we have a lot of channel coefficients to be estimated. So it's very computational, right? And right now, there are mainly two approaches to solve the channel estimation problem. The first one is the semi-passive approach, which means that we actively deploy some active sensors over the surface to facilitate the channel estimation at the IaaS for the IaaS involved links, right? The advantage of this approach is that we can leverage the existing channel estimation approaches, but definitely with the increased cost and complexity. And the other is called a fully passive approach, which means that we didn't change anything about the hardware architecture as well as the energy consumption. And we let the user send the pilot signals and do the channel estimation at the base station. And because we know the pattern of the IaaS, so we can estimate the product of these two links together, right? This is also known as the cascaded channel estimation, which means that we don't know exactly what the independent two links are, but we know the product of these two links. But later we found that a very interesting phenomenon is that for the beamforming design at the IaaS 8 wireless networks, we don't need to know exactly the individual channels. We only need to know the product of these two links. So this is also why the cascaded channel estimation is very popular for IaaS 8 wireless networks. So we have a lot of results in these two papers. And also IaaS as a new component, right? Like relay, active base station, micro base station, how to deploy it. This is another fundamental problem. And we have a lot of considerations and practical factors need to be taken into consideration, right? For example, let's consider a very simple example with the transmitter single antenna and a user single antenna. So how to place the IaaS, right? To place near the access point, near the user, or somewhere in the middle. And here we have some theoretical and simulation results here. As we can see that we plot the achievable rate of the point-to-point link versus the location of the IaaS. As we can see that for most of the cases where D is larger to 2H, the IaaS is optimal for the locations near the access point or near the user, right? This is very surprising because for the traditional relay, we know that if you deploy the relay in the middle, it achieves the maximum performance. But for the IaaS, it is in the opposite, right? So it's very surprising. So this also shows the greater difference of the IaaS as compared to existing technologies like a relay. Fundamentally, this is because of the distance, different channel, signal, and path loss models between these two technologies. Also, for the multiple user transmissions with multiple data streams, we also have to consider another issue like a spatial multiplexing gain, right? For example, if you still deploy the IaaS in the strong line of sight of the access point, the channel rank of from the AP to the IaaS will be very low, right? This will cause very strong interference between the multiple data streams in multiple users, right? So this is also another interesting issue that we need to consider, that is deploying the line of sight or non-line of sight with more scatters to improve the channel rank. And another issue is that when we have a lot of users distributed widely in the network, like we can see here, so shall we deploy a smaller IaaS for each of the user, which means that they will not interact with each other, interfere with each other, right? Or shall we use a large IaaS, right, at the access point, near the access point, to let the multiple users to share this IaaS? So this is another interesting problem called centralized IaaS or distributed IaaS. All of these answers have been answered in our recent tutorial paper. So despite of this, I believe there are still a lot of interesting topics that need to be addressed before a large scale deployment of IaaS in future 6G wireless networks. And for more information on IaaS, you can watch my tutorial video on the IaaS or read our papers or send me an email. Okay, thank you very much for listening.
Thank you, Chin, for interesting discussion on IRS new research direction. So we switch to now Q&A, quickly going through. So the first question is from Wally. Reflecting over terabit speeds, I wonder how practical implementation is going to look like, especially concerning mobility. Is 6G more nomadic mobility rather than today's traditional full mobility? Tommy can answer quickly.
Generally, I think if we implement terabit per second links in one spectrum, one link, we need to go to Josep's spectrum domains. And there we would need a line of sight to a big extent, I think. So with clever beam tracking, we will be able to have certain mobility. If you go on implement or lower care frequencies, I think we might need multi-connectivity and special multi-flow, special multi-streams, like the high-speed trains. There are good opportunities on many wagons there. Yeah, a quick reflections on that question.
Right. Thank you. Emil, you are there?
Yes, I am.
Yes. So there's one question on this. Okay, I'll read it. Could you elaborate on channel estimation for holographic MIMO? I know some works have been. This was asked by Ashkan. I know some works have been done for reflector like lens and develop millimeter wave bands to significantly increase SNR. However, channel estimation is a challenge due to limitation of the field of view for reflectors. Do holographic massive MIMO have the same issue?
Yeah, I think to some extent you can get to some of these issues that we heard about the IRS case as well, because you can view this holographic radio as taking the surface and then co-locate it with the transmitter or the receiver. But if you get rid of that link in between transmitter and the surface, then you simplify certain things. But there's definitely this problem that you can't observe everything, and if you are having a number of different elements connect to the same radio, well then you cannot observe everything. You will have to sort of sweep around and search for different things. So I think there are a lot of opportunities to engineer new solutions, but also try to make use of the best experiences from the hybrid beamforming area as well.
Right, thank you. Okay, let me ask then Josep, next one. This localization accuracy in 6G is better than localization accuracy in 5G. If yes, why?
Well, it will all boil down to the technology that we are implementing. But for example, if I answer from the terahertz perspective, it's just a matter of physics. The higher the frequency, the smaller the wavelength. Therefore, you can see smaller things. But in addition, if you take advantage of the larger bandwidth, the higher the accuracy of that measurement that you are making. If then you further go and say, look, in addition, I'll have more directional antennas with narrower beams, the more directional information you extract to. So there are many reasons why 6G can be more accurate if we design it properly, but the physics help us.
Yeah, okay, thank you. And then there is one question by Matti also for you. Multiband OFDM-based UWB was developed 10 years ago. And NIVAC became a great success due to this high complexity. So the question is, I do like the idea of re-engineering all UWB ideas at terahertz band, but the question is, how do we avoid this issue of complexity? For example, this massive MIMO, IRS, all these things together.
Well, that's a very good question. I can answer partially, and maybe some of my colleagues can help too. But I would say, first of all, so the only reason why at this point, or the main reason why we think we go to the terahertz band is with the promise of bandwidth. If you don't need the bandwidth, probably you don't need to go to terahertz frequencies, even if I love terahertz band, okay? Having said that, if you go to those frequencies, then you have the bandwidth. How do we better use it? Well, I think we learned some lessons out of the failed attempts of ultra wideband. For example, if you ask me, I don't think we should go with an OFDM path. I mean, again, in the context of 5G, everything is OFDM. As we move on, maybe we want to evolve again into single carrier. And if we are really going to embrace sensing, we actually may want to take a look at what the sensing people are doing. And I'm not talking only about pulse communications. I'm talking maybe about chip spread spectrum and other ways to shape your waveform. So I think that there are many opportunities to play. And I don't think we should just get married to what was used. Why don't we think of a clean slate?
Right, thank you. And the next question to Emil from Samarendranath. In terms of mutual coupling, how electrically large array is taken care of it? Taken care of? Is it advantageous in comparison to IRS regarding mutual coupling?
Yeah, so that is also a good question. So if you are, I think there are two different ways of approaching it. If you're going to build a very large array, you don't need to necessarily put the elements at sub-wavelength distance from each other. So you will have the opportunity to have a large aperture, but have like longer distances between them, so you can isolate and get rid of mutual coupling issues. So that's one approach. But if you're going to have small antenna elements or small distances, then yeah, I think we will have to live with a certain amount of mutual coupling. We need to live with that. We cannot use a array response vector from a textbook, but we will need to sort of learn how the hardware is behaving. And I think that AI solutions to sort of understand how the hardware is actually working is going to be utilized to deal with this type of things in practical algorithms.
Thank you. Then from Martin Karas, HHI, was ideal connection between APs and CPU assumed in the cell-free versus multi-cell comparison from to Stefano?
Okay, the answer is yes. Actually, we assumed that there was an ideal connection. But by the way, if you focus on the downlink, the only information that you have to send from the CPU to the access point is the data, because then the uplink channel estimation and the beamformer computation is done locally. So that was the only thing that you need to transmit. And in this way, having a scalable cell-free massive MIMO where not every access point has to communicate with all the users in the network also helps in reducing the overhead of the backhaul, so the bandwidth that is required on the backhaul for the downlink.
Right. Thank you. I think that's about it with the Q&A. I have a couple of slides just to show. From this white paper group, we have a workshop for VTC 2021. The title is this workshop on broadband connectivity towards terabit per second communication. So this call for papers will be coming up soon. The track is open already in TrackChair. The deadline is somewhere in January. We'll keep you informed on this. And then we have continuing webinars coming in. Registration is open for this deep dive into machine type communication towards 6G, which is 11 November. And then the other one is localization and sensing technologies, opportunities and challenges, 18 November. And of course, in terms of this discussion, you can fill in this online feedback form. And then, of course, you can use these hashtags to promote these white papers and webinars. And yeah, thank you. And please check this 6gchannel.com. Thank you very much. That's all.
Thank you. Bye-bye.
Thank you. Thank you very much. Yeah.
Thank you. Thank you all. Bye-bye.
Thank you.